So let's focus now on when a graph might not be a helpful tool and when we can actually estimate limits numerically or from using a table. So let's give ourselves a function. Let's consider the function g of x, and it's going to be a rational function with x to the fourth minus 2x cubed in the numerator divided by 4x minus 8. Now you have a pretty good idea of what a lot of functions look like from algebra and algebra 2, but this is probably a function. You don't know the parent function of this particular guy right here. I can see though in my denominator that if I were to substitute the value 2 in, that would give me 8 minus 8. X equals 2 is going to give us an undefined value. In fact, I can go ahead and say g of 2 is undefined. And as you've probably picked up from our topic or our conversations on limits, that's usually the point we're interested in. And in fact, it is for this particular function. We want to know what is the limit as x approaches 2 of this particular function g of x. And again, I'm not really sure what the graph of this function looks like. So let's build a table of values where we can look at values really close to 2 and see if we can figure out where this is headed. So if I build my table, I'm going to look at x and I'm going to look at g of x values. And I'm going to try to get closer and closer to 2. So I'm going to start off at 1.9. And then I'm going to get even closer. I'm going to go to 1.99. And let's go even closer for this particular function. Let's go to 1.999. I also think it's worth putting x equals 2 on our table. And in fact, we already know x equals 2, g of x right here is undefined. And then I want to kind of mirror these values. So let's look at 2.001. Let's look at 2.01. And then we'll finish it off by looking at 2.1. And I already have the values of these that I've typed into a calculator. So 1.9, if I substitute 1.9 in, I get 1.715, and these all have decimals that repeat for a while. If I plug 1.99 in, I get 1.970, and that's a decimal that goes on. 1.999, I get 1.997, and so on. And I can go in and fill in this other part, and we will here in a second, but if you actually look at the values we have, 1.9, 1.99, 1.99, we actually can already see what the function is approaching, and I can go ahead and write my limit as x approaches 2 from the left, and again this minus sign representing value less than 2. As I'm approaching 2 from the left, my function is approaching the value 2. So I can say that the limit as x approaches 2 from the left is equal to 2. And now I want to do the same approach over here from the right side, and if they match, then I'll be able to say something about the limit. Well, g of 2.1 is 2.315, and that goes on. For 2.01, I get 2.030. And that's a decimal that keeps going on. And then for 2.001, I get 2.003, and that's a decimal that goes on. So as I'm approaching 2 from the right now, you can see that my function values are in fact approaching 2 as well. So from the left, my function is approaching 2, and from the right, my function is approaching 2. And because the one-sided limits match, just like in the previous lesson, I can say the limit as x approaches 2 of g of x is in fact equal to 2. And that's the answer that I'm looking for that particular limit. So I didn't need a graph. In fact, it was easier for me just to get values out of a table. Keep in mind, at 2, my function's undefined. But when we talk about limits, we don't really care about what happens at x equals 2. In fact, we can go ahead and just kind of cover it up for us to be able to see what's happening from a limit standpoint. And you can see that as I close in from either direction, my function is approaching the value 2, and that's what makes that particular limit statement true.